Okay, everyone, welcome again for some of you to the second presentation by Bob Shishko, who the other evening talked a little bit about some of the off-Earth mining projects on Mars. This is going to be a little bit more
academic,
system engineering, sort of academic type presentation, but it's all part of a very busy couple of weeks that we have. We've got a couple of presentations next week, big public presentations by other visitors from NASA and ESA. Serkan here is running the Future Mining Conference next week, and we're running the Off-Earth Mining Forum. And it'll coincide with the Future Mining Conference, and there'll actually be a couple of joint sessions there where we'll be talking about space and mining at the same time. But today, I'd just like to introduce Bob. He's the Principal Systems Engineer Economist in the Project Systems Engineering Formulation section at JPL. He teaches Space Systems Engineering, Logistics and Economics at the International Space University. He's worked on operations and logistics issues for NASA's major human space flight projects over 30 years, including the Space Station Freedom, Space Station, Constellation, as well as JPL robotic missions to Mars and Jupiter. He's one of the founding fathers of the Project Design Center at JPL, and as a principal contributor to and task manager of the NASA Systems Engineering Handbook. He was awarded the NASA Exceptional Achievement Award, and in 2012 served as Chief Scientist, Infrared Space Systems Director at US Air Force Space and Missile Systems Center. He's got a position at USC and has authored portions of 6 books and so on. Right, so basically Bob's been working with us on an off-Earth mining project with Carlos and Serkan and myself and some other people. Very, very interesting stuff about mining water on Mars. But today we're talking about supply chain management. Over to you, Bob.
Okay, thank you. So this is basically one of the lectures that I give at the International Space University. And part of the reason is that increasingly logistics, space logistics, is going to be an essential part of the human expansion into the solar system. So I would like to, let's see, get this going. So I'm going to talk a little bit about why we should care about interplanetary supply chains and space logistics, and a little bit about how those considerations enter the system engineering process in the development of essentially a system of systems that will enable humans to explore the moon and eventually explore Mars. And the way I'm going to do that is to introduce you to some of the fundamental concepts of interplanetary supply chain management and space logistics that have been very successfully applied to modeling alternatives for NASA to build lunar outposts or get humans to Mars. So at the end, I'll talk a little bit about the strategic issues and trades and some of the very recent relevant literature. One of the reasons this came about was over the period of time that I worked on Space Station Freedom, International Space Station, and Constellation, it became increasingly clear that we needed to develop space logistics as an academic discipline. And so I work very closely with the Department of Aeroastro at MIT. And as a result, there's a program in interplanetary supply chain and space logistics. And they've awarded a number of PhDs and several dozen master's degrees, focusing on the academics and modeling of interplanetary supply chains. So there'll be a lot of new concepts that I hope to introduce you to in this talk. So why should we care? Well, about space logistics. Well, More than 10 years ago, headlines, you see read that we're going to have to abandon the space station, the International Space Station, because supplies were so low that the logistics and the inventories of food were not being replenished, and we might have to abandon the space station. And you would think that those kinds of problems might go away. But just this year, we had a failure of the Cygnus capsule to reach the station. We then had another failure unexpected, really. SpaceX failed to launch one of their Dragon capsules to the space station. And then even a very usually reliable Progress vehicle from the Russian Space Agency also didn't make it. So we had 3 failures of the supply chain in the period of about 6 months. So it's still a very relevant issue. NASA has a term we call dissimilar redundancy. And even with this dissimilar, double dissimilar redundancy, we still failed to resupply the space station. So logistics is not only a persistent issue, it's also an international issue. Now, if some of you have seen kind of the space movies like 2001 or most recently The Martian, okay, spaceships don't really look like they do on the Hollywood set. This is actually the space station. And so what you see there is during Expedition 11, we had crew member John Phillips in what is called the joint airlock. And you can see what it actually looks like. It's basically an inventory, it's a warehouse for all kinds of things that are needed to keep the space station running. It's not only that, but on the left-hand side, that was during STS-114. You could see what Node 1 looks like, and on the right, it shows a view of the pressurized mating adapter that links the Russian segment and the US segment. And you're looking towards the Russian FGB. Well, what the PMA, pressurized mating adapter, is largely used to store clothes, hygiene, and towels. So it's a closet, basically. So this is what actually things look like. Kind of messy here. This is inside the Russian FGB, functional cargo block, during that same STS-114. It's kind of crowded and a little disorganized. That's the way things are. The US since has added a pressurized, essentially a multi-purpose pressurized logistics module just for storage. The Russians have also added a small pressurized module for storage. And the European Space Agency's ATV is also used for storage. In fact, it's actually one of the better places to sleep if you're an astronaut because it's quiet. So the idea is that logistics is still an issue even today. But again, why should we care? Well, logistics is what enabled Antarctic exploration. It was the ability to maintain a scientist and the equipment in place and sustain their scientific work. Before 1925, the techniques were basically unchanged for 100 years. Dog sled was the primary means of transportation. But after 1925, the development of mechanized transports, airplane, radio, that really enabled access to the Antarctic continent, to travel within it and to survive in that kind of hostile environment. Well, the lessons from Antarctic apply to the settlement and colonization and exploration of the Moon and Mars as well. So recent, perhaps you've heard of Mars One. I don't know if that's an enterprise and it's based in Holland to send people to Mars as colonists in the year 2023, although they recently slipped that. And then there was some recent media attention that focused on the flawed Mars One approach because of inadequate attention to logistics, among other things. So that work actually came out of the MIT space logistics program, that analyses, and it received considerable media attention, as I pointed out in my first lecture. So, in fact, we need to basically treat logistics as an important part of the system engineering process. Okay. So about 10 years ago, we basically put together this chart of uses of interplanetary supply chain modeling and for the Constellation program. And we kind of try to educate NASA on why we needed to do this kind of academic work. And what's amazing is that it still applies today. Even though the Constellation program was canceled, there is an ongoing work to, at least within NASA, focused on getting humans to Mars. Because our other traditional partners, like ESA, JAXA, and so on, want to focus more on the moon. But in any case, what's still needed within the system engineering process is the ability to analyze the supportability requirements. Can you sustain a lunar outpost? Can you sustain a multi-mission campaign to Mars? And that's going to rely a lot on logistics. So in fact, what we need to do is to kind of look at all the aspects of space logistics and supply chains. We have to look at the network level questions. What is the optimal logistics network? How should we design the individual elements like Orion in terms of commonality with other systems, interfaces and interoperability, kind of reliability, maintainability, stowage issues, the kinds of things we see on the International Space Station. There's also a question of how much inventories and what are the optimal safety stocks that need to be pre-positioned before humans attempt a landing on Mars. There are trade studies of the subsystem technologies. For example, do we design the environmental control and life support system to be fully closed, or do we have a certain amount of it open, and therefore we need to supply essentially things like water and air to those systems. So the design of the individual elements in terms of their technologies is something that is actually within the realm of space logistics. We also have to worry about what I talked about earlier. What if analysis? What if there's a network failure? What if you have 3 failures of dissimilar logistics supply vehicles? Keep in mind, this was 10 years ago we wrote this. And this is what we talked about on Tuesday. What is the cost-benefit analysis, or what is the profitability potential of in-situ resource utilization, essentially mining for local resources, whether it's on the moon or Mars? When does that make sense? That is part and parcel of space logistics. And lastly, what about strategic commercial relationships? And how much should NASA, for example, rely on commercial companies like SpaceX to support their human spaceflight? So even though this was 10 years ago, we're still asking these questions. Then once you actually have a program in execution, in operation, you still have space logistics issues like managing the inventory, keeping track of the various commodities and resupply schedules, essentially what items need to be manifested. And here, of course, information is a key to execution. So these are the kinds of topics that get studied in within the space and logistics and interplanetary supply chain management discipline. So let me introduce you to 4 fundamental concepts that we use in modeling these supply chains and logistics issues. So the first one is really about the network. So this is kind of a terrestrial enterprise logistics problem. It's where to place warehouses. What capacity should those warehouses be? What items should be stocked in those warehouses? And how much of each item should be stocked? So inventory is very important, but there are constraints. Constraints on customer waiting time. How long is a customer willing to wait for an item, like when you order from Amazon? Do you want it in 6 hours, or are you willing to wait 3 to 5 days to get that? So those are the kinds of issues when it comes to inventory. Also, how to ship. When you have multiple means of shipment, each has a different time and dollars associated with it. What's the best way to essentially move inventory across the transportation links? So these are the kinds of things that are addressed in basically business schools and supply chain textbooks and courses. So the modeling of a supply chain is essentially a network modeling problem. Go back. Okay. So, this is actually done on a regular basis. There's software that enables you to do kinds of planning and execution. And basically there are 2 modeling techniques that are used. One is optimization for planning, and the other is simulation during execution. And these kinds of issues that generate the network graphs that you see. But in space, the issues are quite different. What makes designing a network, a supply chain network, in space different is the network characteristics and the transportation constraints. So this is what the supply chain looked like during the Apollo era. Everything was launched with the mission. These are the Apollo missions that actually landed on the moon. Everything was launched from the Kennedy Space Center. They went to different locations on the moon, and everything that you needed was brought with you. So that's what that network graph looks like. Space station, a little bit different. We have now multiple sources of supply. KSC, we have from Japan. We have from Japan and Baikonur and Guyana. So we have different launch vehicles, different transfer vehicles that are used. They all go to one location, and they essentially resupply the space station as needed. With food, in some cases nowadays small spare parts and so on. Obviously payloads are as well. But the future is going to be much more complicated than that. And so, this is kind of the picture of what we thought might happen in Constellation. This would be a lunar outpost somewhere near the south pole of the moon, and there would be other sorting locations, perhaps ISRU locations on the surface of the moon. This would be low Earth orbit. Low lunar orbit. This would be low Earth orbit. We might have expeditions that we sent to a near-Earth object, such as an asteroid, and eventually Mars. And these, of course, were the terrestrial locations. And we still have the International Space Station flying. So the network is going to be considerably more complex in the future. In fact, what's interesting is that even though this diagram is only about a year or a year and a half old, low lunar orbit is no longer in favor. We now have some new orbits that are attracting a lot of attention. One of them is called a distant retrograde orbit around the moon. Roughly speaking, it passes through the L1 and L2 Lagrange points, about 70,000 kilometers from the surface of the moon. And it's in favor because it has a great deal of stability. You need very little delta V to maintain a system in that orbit. Another orbit that's also gaining attention is called a near rectilinear orbit. That one essentially kind of is in a plane that is perpendicular to the kind of Earth-Moon axis. And it goes over the north and south pole of the moon. And it also is a fairly stable orbit with a low delta V maintenance requirement. So these networks, even though this is fairly new, might include orbits that we haven't thought of yet. So those are part of the network graph that we may have to explore as part of the trade space. But as I said, what makes designing an interplanetary supply chain different from designing an Earth supply chain is the network characteristics. So, as most of you know, there's a trade-off between delta V and time of flight. And it's really delta V, not distance, that's really that matters in space travel. It's also the time-varying nature of some of these operational nodes within the network. Particularly as you go to interplanetary distances. As you know, the launch window to Mars occurs about every 26 months. So you have to take that into account in designing your network. Furthermore, it's not just mass and volume that are important, but we also must deal with a very inhospitable environment. Both thermal, radiation, and so on, particularly if we're going to transport humans. So that's the key point, is you have to design and be capable of analyzing a network that takes into account all of these characteristics and constraints. So, how do we build such a network? Well, first of all, we start off with the nodes of interest. And these nodes can be terrestrial locations, but they can also be surface locations on the moon or on Mars. They could be Phobos, it could be a near-Earth asteroid. So these are all the physical nodes of interest. But also they can be orbits. The nodes within a space network can include various orbits, particularly specialized orbits that, as I mentioned, the DRO and NRO. There are also Lagrange points that are nodes in a space network. Lagrange points, as you know, are places of particular interest as they provide a sort of gravitational equilibrium. So we start off with a set of nodes of interest. And then we connect those nodes with what we call static arcs. So you can see some of the, it's a little dim on the screen here. But basically these are the feasible paths from one node to another. Okay, and each of them has a delta V associated with it. So those arcs are, as I said, are governed by orbital mechanics. They have a delta V and a time of flight associated with it. And it's the delta V between these nodes, not the distance, that's important. And the time of flight between these nodes may depend on actual time. When you depart determines when you arrive, kind of the pork chop diagram. Now, the way we deal with orbital mechanics is that we introduce the notion of a time-expanded network. So this allows the consequences of orbital mechanics to be captured while preserving the advantage of a network representation for supply chain modeling. And I'm going to show you how that works. So a time-expanded network. You start off with the static network consisting of the physical nodes of interest and the feasible arcs that connect them. Okay? But now what you do is you define the nodes in space and time. And now the feasible arcs then become, in this time-expanded network, have the following properties. They must exist in the static network. They move forward and only forward in time, and they represent feasible orbital mechanics. So here's an example. Let me start off with very simple example, 3 static nodes. Low Earth orbit, low lunar orbit, and the Earth-Moon Lagrange point 1. So those are the static nodes. We can define the arcs. The static arcs that go between them, and for example, what I'm sort of showing here is that to go from Leo to Earth-Moon Lagrange point 1 takes anywhere between 3 and 3.7 days. Okay, to go from EML1 to low lunar orbit can take between 1.8 and 2.5 days, and similarly to go between Leo and LLO. So. Basically this is dictated by orbital mechanics. So what does the time-expanded network look like? So here's what the time-expanded network looks like. We have time moving down here, starting from day 1, day 2, and so on. I'm going to just look at 5 days. We're going to have our different locations. So this one is Leo, this one is EML1, and this is low lunar orbit. These arcs, okay, represent all the feasible network, feasible transfers between these nodes. So you can see over time, low lunar orbit is moving, but you can go from here from low Earth orbit to Earth-Moon Lagrange point 1 in about 3 days, as shown on this diagram here. So that is right here is the feasible arc in a time-expanded network. So what this allows you to do is to build a network that incorporates the orbital mechanics already. And that's very important, particularly the further you go out. Now here I've shown a time horizon of 5 days and a discretization of 1 day. Now think of the problem of having multiple missions to Mars, both cargo and humans, and that may take place over a 12-year period. Dealing with it 1 day at a time makes the network actually computationally too complex, even for current software. So there's actually been one of the PhDs at MIT developed a very clever way of looking at short discretation for some parts of the mission and much longer periods for things that are not as, you don't need the detail. So you were able to reduce the computational load in that particular time-expanded network. So this is what is in fact used, and at the end I'll show you some papers that actually spell this all out in much more detail. So the first fundamental modeling concept is that of a time-expanded network that incorporates orbital mechanics. The second fundamental concept I want you to be familiar with is called classes of supply. And during our work on constellation, we developed a classification system that included 10 major classes of supply and about 43 subclasses of supply. And this is needed in order to define essentially the inventory management, but also the modeling, because when we send a spacecraft from one arc to the other, it's going to be carrying multiple commodities. And of course you have to meet all the constraints that are implied by that. But it's important to understand that we need to deal with each of these classes of supply. So propellants are fairly obvious. Crew provisions include things like we saw in those photos early on: food, clothing, hygiene items, oxygen. Crew operations consist of things like laptops, EVA equipment, health equipment and consumables, safety and communications equipment. Maintenance and upkeep includes spares, maintenance tools, batteries, filters. Exploration items are field equipment, scientific instruments, waste and waste management. I'll leave that to your imagination. Infrastructure. Infrastructure would include major end items, including the carriers and propulsion modules that would be used those can in fact be considered a particular class of supply, a separate class of supply as well, for modeling purposes. Miscellaneous, sorry, let me go back. Miscellaneous, well, flags. We've got to carry a flag. Okay. Now, we base these classes of supply on things that have occurred before. The military uses classes of supply. There's various different standards for those. But this grouping was largely based on function. What does the item do? And the nomenclature we took from what's called the C-card, which is actually what's used on the International Space Station. The C-card stands for Consolidated Commodity Allocation and Requirements Table, a typical NASA acronym. So, as I said, 10 classes of supply, about 43 subclasses. Keep that in mind now. The third fundamental idea is the equations and constraints that govern these commodities as they move along a space network. Obviously, one of the most important is the mass balance. And this essentially constraint basically says you can't consume more than you have. And that's represented, by this kind of equation. So commodities, we have to deal with the fact that commodities are stored at a node, but the capacity of that node may be limited. Commodities may be switched between carrier elements. In fact, that's part of what we do in space station. We send up supplies, they get transferred to the pressurized modules of the station, and then the carrier vehicle essentially is either returned as in Dragon, or it's burnt up as in Progress. We need to account for gains and losses that may occur along a transportation arc. Obviously, a big one is kind of that we in an impulsive burn, we lose propellant. You may have boil off, or very simply, astronauts eat food. They consume the food along an arc as they travel. So we must take that into account. But so you may lose a commodity, but you also may gain a commodity because of in situ resource utilization, as well as in space refueling. So we need to take that into account. And this is kind of the basic equation that does that. And this particular property here is used to applies to certain kinds of commodities like food. The crew eats a certain amount of food per day, and so you need to subtract that based on the amount of time needed to travel from one node to another. Some of the work that another PhD that was awarded at MIT actually turned this equation into a series of matrix equations. which is very innovative, and that allows you to track what happens along each arc, as well as accounting for ISRU in space fueling, propellant boil-off. And in fact, in the case of an impulsive burn, it reduces to the rocket equation when you have the right matrix in there. So, so this is actually one of the most fundamental equations in space logistics. And so obviously what you try to do is design your network and design the flows so that you actually meet the demands at every node. But there are other constraints as well that we have to consider. One of them is the capacity of the carrier elements to move payload, if you will, and commodities from one node to another. So they must be able to accommodate, obviously, the mass and volume constraints within each transfer. We have compatibility requirements that have to be met. For example, humans and radioactive material are not allowed to be put on the same carrier. That's just a rule that NASA has. So you have to, you can't just load plutonium on, onto a human transfer vehicle. But also, even more, or just as important is the fact that you cannot put a flammable or something that has perhaps introduces an element of danger to one commodity. It has to be put on a carrier for which it is certified. Okay, so you can't just stick something on any carrier. It has to be a carrier that is certified to carry that particular commodity. Another constraint is the capability. Can you actually launch a stack of carriers? Is your launch vehicle powerful enough to get out of the gravity well, essentially? And further, can a particular element that you're intending to land on the moon or land on Mars, does it have the, can it perform that kind of transfer? For example, from high Mars orbit to the Mars surface, well, you've got a couple of ways of doing that. You can either carry a lot of propellant and land, or you can reduce the propellant requirement by essentially aerobraking and having an aeroshell as well. So you need to be able to account for that when you do a transfer from one node to another. And lastly, constraint on priority and timing. It doesn't do much good to provide a lot of food after the crew is already starved. So, which seems to be the case in Mars 1. So you have to make sure that you can meet the priorities of the that are required, the timing restrictions that are required by your mission. So these have to be modeled in equations in order to do an optimization. So it gets fairly complex very quickly. And I'm going to show you why. So the kinds of basic data that you need include, obviously, the launch vehicle specs to a target destination or target orbit, and the availability constraints on that launch vehicle. And then on your carriers, these are kind of fundamental information that you need to do the modeling. You need to understand the tare mass, what is the max payload and volume that you can take, how much is pressurized versus unpressurized, what overheads, what we call flight support equipment, attachment fittings, accommodation mass, on-orbit shelf life, max down mass. Do you have late access? What are the docking constraints? And what are the subcarriers that go on a major carrier? So this is just raw information that you need to have in order to do the modeling. So, you know, it gets fairly complicated when you look at delivering a simple orbital replacement unit. There's basically a whole bunch of other equipment that may be needed in order to complete that delivery. And these are all elements of analysis that you need to have. So we have an equation that we used for modeling the traffic to the International Space Station. And perhaps you've heard over the years that the shuttle delivered 6 metric tons of material to the space station. Well, you're thinking, space shuttle capable of launching, 20,000 kilograms. Why did it only get 6 metric tons, 6,000 kilograms of material to the space station? How is that possible? Well, when you start looking at all the things that you need to take into account, let me give you an example. So the total payload to the capability of the STS to 407 kilometer orbit, 51.6 degrees, and that's key because that, the higher that inclination, the less capability you have, is about 17,055 kilograms. But then you have to subtract the STS overheads, and that included fixed overhead of 2,288 kilograms. And then you had some flight-specific overheads, which were 340 kilograms. And then you had the module that the actual carrier, the MPLM, that was actually carrying the commodities, and that weighed 4,491 kilometers. And then the accommodations within that MPLM were 3,144. So what are you left with? You're left with 6,800, roughly, 6.8 metric tons. Unfortunately, you have to now attach the MPLM into the shuttle bay, and that eats up another 492 kilograms. And then you have to have your umbilicals, the remotely operated electrical umbilical and remotely operated fluid umbilical, and that also costs another 372 kilograms. And what are you left with? 5,928 kilograms of actual cargo is able to go up there. And that's only this part. Well, that's the best you can do. This may make it even worse. So what's on that side of the equation? On that side of the minimization, or the smaller of, you've got a MPLM that is capable of carrying 9,071 kilograms. But again, you have to subtract off the accommodation mass of 3,144, and you're left with 5,927 kilograms. So somehow, fortunately, these two numbers are about the same, just under 6 metric tons. So you need to have all that kind of information just to figure out how much you can actually launch on a particular launch vehicle. Okay, so now the fourth and last fundamental concept is what we call supply and demand modeling. So basically what this is you need to be able to forecast how much of each class of supply will be needed to meet an exploration goal. And what is this driven by? This is driven by the ops concept, the supportability targets, the crew size, the infrastructure to be supported, what safety and risk and reserve policies are in effect, what specific technologies are chosen for the infrastructure subsystems, like the environmental control and life support, what are the reliability, availability, and maintainability requirements for major infrastructure items, and what are the mining opportunities, the ISRU, in situ resource utilization, that are available and can be exploited. So you need to take into account all of these in order to get what is that demand that goes into my mass balance equation that we had. Well, looking at a number of commodities here, propellants, spares, crude consumables, and so on. Here are the factors, that we just listed, and some don't play in it, and others do play in it. If we looked at spares, you can see almost everything is important in estimating the amount of spares. That's one of the things that the Mars One people never did, and the MIT people found out that they couldn't deliver enough spares with their approach. So how do we know that? We have equations. So here, just to model the spares demand, we start off with a very simple equation. This is actually the expected number of failures per day for a particular orbital replacement unit. So basically a box, for example. So we have a duty cycle, we have the MTBF, and a K factor, which is a fudge factor that enables you to take into account particular environmental conditions in which the ORU will operate. And for each ORU we want to estimate the number of failures, the random failures between a given time period, and that's the failures per day times the quantity per application on a given element, and then the number of elements that make up the Mars base or the lunar base or the International Space Station, times the resupply cycle. So those are the number of failures, or expected number of failures, that you're going to have to deal with. Of course, expected value is not the whole distribution. You could have a really bad day or a bad month and have much more failures than that. But we can actually make that calculation as to the standard deviation. But this is the starting fundamental equation, and then you have to add all this up. Once you know the number of failures, you can estimate the total mass and volume that has to be delivered, and that goes into our other fundamental equations that we have to worry about. Unfortunately, things even get more complicated, and I know at least in space station, they tend to use they have to estimate the number of reserve spares that they want to have on the station in case there's a missing resupply cycle or there's an immediate emergency. And so they actually use an availability objective function. And this gets much more complicated because now the availability depends not only on those failure rates, but it's a function of all the spares you have. And you have to calculate essentially the number of expected back orders based on those number of spares and the failure rates, which is lambda here, subject to some sort of constraint. It could be either a mass or a volume constraint or a dollar constraint. Okay? So we actually have to solve these kinds of equations in order to get the optimal number of spares. So again, the modeling of every commodity within all those classes of supply. You have to have an approach, a modeling approach. You have to have a set of equations in order to estimate the total demands that you're going to have at each node. So those are the fundamental concepts and how we try to deal with them. Some of the strategic issues. The first one is interesting because we are actually dealing with that now as NASA tries to transition from, since the end of the shuttle program, to having essentially commercial companies provide delivery of these commodities to the space station. This is both SpaceX as well as orbital ATK. So, what is the right balance in NASA's role versus turning it over to a commercial enterprise? Same thing on Mars or the Moon. How much are we willing to turn over to commercial companies to provide certain commodities to astronauts or colonists, astronauts on the lunar outpost or colonists on Mars. So another question is, how do we deal with the idea of reserves and moving these commodities? And one of the concepts within supply chain management is the push-pull boundary. The general idea here is that for commodities whose demand can be well estimated, basically you want to push those commodities automatically. When the demand for something cannot be well estimated in advance, then you have to essentially wait for the demand to arise and then you push them that way. So that comes from terrestrial supply chain management concepts, and there's an equivalent in space logistics as well. Now, we also have to deal with new forms of propulsion. NASA has recently incorporated solar electric propulsion into its plans for Mars. And with the high power solar electric propulsion, we can move as much as 40,000 ton pieces of infrastructure to Mars. Of course, it'll take about 4 or 5 years to get there. It's slow, but it actually is a kind of very high, efficient, high ISP form of transportation. So how do you take advantage of that within the supply chain? That gets back to the push-pull boundary. You're going to be able to push a lot of stuff forward, like food and medical and other things for which the demand is fairly well known, or is going to be fairly well known. Logistics information architectures. How do we coordinate among international partners? How much do we rely on automation to tell us what's needed on board the spaceship? Reusability and commonality and reconfigurability are also issues. There's a cost for some commonality. On the other hand, it may have big savings in terms of the interplanetary supply chain, so there's a trade-off there. We have new technologies such as additive manufacturing, which could dramatically change the way we deal with spares and other in situ manufacturing. The repair strategy is important. On space station, essentially the repair strategy was pull out the box, put in a new one, ship the old one home. The astronauts were not really intended to repair. On the moon, in Constellation, the lunar outpost, the astronauts were going to have to repair those things because the supply chain that we had in space station wasn't going to be there. We were going to get 1 or 2, maybe 3 missions a year to resupply the lunar outpost. So you have to think about what is the optimal level of repair. And lastly, what is the return on investment of mining in situ? How can we make, does it make sense to try to provide water on the moon from lunar resources? First, you have to find it, you have to be able to extract it, move it to the location where the demand occurs. So there is a strategic issue there of what's the right amount of ISRU. Okay, so again, as a summary, I've talked about a lot of different essential elements of analysis. I think you can sort of take a look at this list and understand that in order to do optimization for planning purposes, there's a lot of information that has to be brought together, a lot of equations that have to be brought into the analysis in order to get sensible results out. And these are some of the recent papers that have come out of the MIT Interplanetary Supply Chain program. This one lays out some of the things I've talked about in this lecture. This is the one that explains time-expanded networks and received quite a bit of attention recently in NASA because the conclusion was that the road to Mars goes through the moon by the use of lunar water converted into propellant. That could provide could reduce the amount of mass that would have to be launched from Earth by as much as 43 to 46%. But of course, we have to understand exactly where that water is on the moon and how it can be extracted. This is the now famous paper that debunked the Mars One approach. It was done by Sidney Doe, who is actually from Sydney. He went to that other school down across town. He's a graduate student at MIT. It's an interesting paper. And this one is just coming out, discusses the notion of a multi-commodity network flow. So these are some of the key papers in this area. And if you want to learn more about that, there is a nice website to go to. And I thank you.
Yeah, some of us are a bit pressed for time, so we won't be able to have a huge number of questions. Or none.
I suspect you can learn a lot from navies and submarines, since they're very similar, closed volume and inhospitable place for long periods of time.
Yes, in fact, early on in Constellation, they did actually look at how 90-day deployments, what the Navy does to handle that. But I never saw any results that came out of it.
And also how to pack things inside.
Yes. But Navy has got at least 100 years of experience on submarines.
Have they applied that model of spare demands, that equation, on simulations that they proposed, and what were the spare parts that actually came out as the highest bid demand?
I think that is actually done in the Sidney Doe's paper. I think it's actually done in this paper. He does spend a lot of time on estimating the spare, so it's easy to get a copy of that. I guess a lot of food for thought. Okay.
All right, well, if there are no questions, that suits those of us that are a bit pressed, but let's thank Bob again. Thank you.